This is a part 2 of ortho-para directing groups, or in general directing groups. So in the part 1 we studied this CH3, which is electron donating by nature. So if we go ahead and put it on the benzene ring, then the carbocations we are getting here, if you do recall, if we go ahead and react it with the electrophile, this benzene ring will attack on the electrophile, and we have three possibilities. We discussed all of these. And if we have the substitution on the ortho position, which is just one carbon over, and then what will happen here is that so we are getting the plus the carbocation directly under the electron donating group. So these are the intermediates and during the electrophilic aromatic substitution. So these intermediates, we do know that these are rate determining steps. This is the slowest step because this is energetically unfavorable. The aromaticity of the benzene ring is being compromised, which is very stable. So and this is providing a large energy barrier. So in order to put this electrophile here on the benzene ring, and there is a large energy barrier that is provided for this reaction. So what is happening here when you put carbocation directly under the electron donating group? So this plus charge is being neutralized by this electron donating group over here on this position. So we do get the carbocation under directly the electron donating group, which is balancing the intermediate and thus trying to lower the activation energy or the energy barrier for this reaction to proceed, and thus making it favorable to happen. So, and if you go ahead and check the para position as well, so you do get one of the resonance structures where what is happening, you are directly getting again the carbocation under the group, which is balancing this positive charge of the benzene ring of the intermediate, and which is a balancing effect, which is making it more energetically favorable. Uh, okay, so when the things are getting stabilized, that is something requires less energy, and whatever requires less energy is more favorable to happen. So however, what is happening here in the meta position, you are getting the carbocation every time you're missing this electron donating group, you're never getting it on the directly under the electron donating group. So this plus charge of the benzene ring is not compensated. This methane, this alkyl group is unable to stabilize this plus charge of the benzene ring, and hence making the conditions the worst for the this reaction to happen or proceed further. So we do want to learn here that whenever we are trying to put the electrophile on the ortho or the para positions, the plus charge or the carbocation is facing a stability effect due to the due to its position directly under the electron donating group. So there are some other groups as well apart from CH3, for example OH. Okay, they donate. This is a better donating group than the CH3. It is just there is the polarization of the bond is here. It is just donating, not actually donating. It is just stabilizing this by hyperconjugation. Here it is actually donating the lone pair to the benzene ring. You will just see in a while. I will go ahead and draw it for you, and where we will learn that this is a better electron donating group as compared to CH3, and we will learn. Let's go ahead and draw that. So let us learn about activating groups. Now we just learned that if you put a methyl group or this another electron donating group, which is OH group, then why they're called ortho para directors? Because we just learned that whenever we do the substitution at ortho and para position, we do get the carbocation directly under the group that will stabilize that carbocation, in contrast to the meta position, where it is never directly under the electron donating group. So we just learned that CH3 group, it is electron donating by the effect of hyperconjugation. And what we will see here is that in case of OH group, it is it is electron donating by resonance effect. So we will have one more resonance structure here, and this will actually donate the electron pair and participate in the resonance. So let's go ahead and check that. The OH group is orthoparadirective because it is electron donating. So this O has a lone pair, which can actually donate the electron pair here. Okay, compensating this plus charge on this carbon and becoming itself positive. So what you can see is this plus charge moved all the way up to the oxygen. So the more this charge you can distribute on the molecule, the better is the stabilizing effect. And these are the intermediates. And these intermediates, this OH, the presence of this OH group is lowering the energy, uh, and thus directing the electrophile on the ortho or para position. By doing so, it will it will decrease the activation energy. It will make the things more favorable for the incoming uh, electrophile. So as contrast to the meta position, which is here, so you just saw we are getting the plus charge over here, here, or here, never directly under the electron donating group. This is for the meta positions I'm drawing, and so you can see here this is not something stabilizing the plus charge of the intermediate and thus doing nothing. So this OH group is able to do nothing for the meta position. Now moving on, let me clear this up first. Let's go ahead and check one more electron donating group. So this is another example, which is the amine group here, which is also electron donating by resonance. It is stabilizing the carbocation directly under it. So that is why the electron donating groups are also called orthopara directors, because they facilitate this carbocation here. They facilitate the reaction, because these are the intermediates, and this is very slow step. And if anything stabilizes this positive charge, this intermediate ions, then that is lowering the energy and making the things more favorable for the reactions to proceed further. So if you go ahead and check here, this the lone pair on the mean group on the nitrogen will go ahead and move here and directly stabilizing this plus. So this plus moved all the way up here because nitrogen donated its lone pair, so he has this formal positive charge now. So the more the charge can move over the molecule, the more stabilizing effects it leads to, and energetically that is more lower in energy, right? So that is something everyone is looking forward for less energy. So these are also called not only orthopara directors but also activators. I wrote here activating groups previously. So electron donating groups, they are activators for electrophilic aromatic substitutions because they're activating the ring. They're making it more feasible for the reaction to make it happen, because they're stabilizing the intermediate, which is energetically very you can say costly step, and they're lowering the energy for that thing to happen. So they are not only orthopara directors, but they are also activators. So you just learned about OH, NH2. So you can also say that we're gonna write here, so the OH and NH2, they're better orthopara directors uh, as compared to the CH3, because they're actually donating the lone pair, participating in the resonance, whereas CH3, it is just stabilizing the plus charge with the help of the hyperconjugation. So moving on, let's learn about meta directing groups. here we have an example of electron withdrawing groups. Why do we call it deactivating groups? Let's go ahead and check that. Because this is your nitro group. So there is a plus on the nitrogen. So we have told whenever nitrogen has four bonds, it has a common positive charge. Now what will happen here? If you go ahead and do the ortho substitution, the electrophile go ahead and seeks the ortho position. So we do know that one of the intermediate, the resonance structure of the intermediate will yield the plus charge on this carbocation, on this carbon, which is directly attached to this nitro group, because this is an electron withdrawing group. Why is that? Because nitrogen is carrying a formal positive charge. Nitrogen is an electronegative element, and to stabilize its positive charge, it will go ahead and seek electron density from whatever it is attached to. Okay, it will look forward from the electron from the thing it is attached to. So it is seeking the electrons from something which is very which is already positive, so which is further destabilizing. This is not something very favorable situation. This is leading to some more destabilizing situations. So destabilization means it is going to cost you a lot of energy, okay, and thus it is energetically less favored. So ortho, and also for the para positions also, one of the resonance structure of the intermediate ion will yield the plus sign directly under the group attached here, right? So again, the same situation will happen. The destabilization will happen, which is not energetically favored. So thus this let's look into the meta position. If you go ahead and substitute your electrophile at the meta position, so this plus charge will be either here or here or here. If you recall from the previous lecture, so you are going to get carbocation here, here, or here, never directly under the electron withdrawing group. So this is not energetically favorable, but it is a less destabilizing situation as compared to the ortho and para positions. So this is so whatever is stabilizing a little bit. So this meta is more stabilizing than this one, although it is not being compensated. However, it is more stabilizing as compared to the ortho position. Um, this meta position will be more favored. Okay, so electron withdrawing groups I've written here, they are meta directors. Okay, so they will be directed towards the meta position, as this is going to cost less energy as compared to ortho and para positions. So why do we call it deactivating? Because the nitro group, it is electron withdrawing. It is further deactivating the group, the benzene ring, because it is withdrawing the electron density towards itself, further destabilizing the uranium ion. Because here we generate the carbocation, and it is already positive, and something which is further taking away the electron density from which is already positive is causing further destabilizing effects and making it more less favorable to happen. So it will raise the energy bar even higher. Okay, for the this intermediate step to take place further, to go forward. So this is raising the energy bar, the electron withdrawing group, making it more positive, is even worsening the situation, thus even increasing the activation energy. Okay, for the electrophilic aromatic substitution. So for electrophilic aromatic substitutions, electron withdrawing groups are known as deactivating groups, and they are always meta directed. Okay, now let's look into one more example, one such example. So here we have another example of carbonyl group that is attached to the benzene ring. So if you go ahead and attach it, so this is benzaldehyde. This is the aldehyde group that is attached here. So if you go ahead and attach your electrophile at the ortho positions, then you do know that you get the carbocation right here. Okay. Then what will happen is this thing. Since this carbon, if you look over here, this carbon is attached to oxygen, which is electronegative. Okay, so this carbon is partially positive, and this carbon will try to. I will go ahead and put a plus sign here because this is carbocation. You're going to get one of the intermediate like this when you attach your electrophile at the ortho position. So what will happen here? So carbon will try to extract the electron density from the ring, okay, which is already positive. So you get the plus and you get the electron withdrawing group. And now you understand why this carbon is electron withdrawing, because it is attached to this oxygen, so it is becoming electron withdrawing. So what will happen? So this bond would move here. Okay, you can shift the bond electron density here. So this would move here, this would move here, and this would move here, so generating this thing here. So you do get the plus charge here, since it left, this one left over here. Okay, and then what happens is, so you do get two plus charges in this ring. Okay, here we do want to make some change with the charge over here. So let's say we have this charge here instead of there. Okay, so because you do know that you get here, here, or here. Okay, uh, in the ortho position. So let's say you have the charge here, so that would be a better viewpoint if you put the plus charge here. So that would be more easier to understand why it is even more destabilizing. So you get the two plus charges here, so one is already here, and since this double bond moved here, this one moved here, this one is forced to move here, and that would push this bond to the oxygen, generating this negative charge here. So since this one left, okay, so you get this bond here, right, and the double bond C, and then you have this plus charge here, so you do get two positive charges here. Okay, and also again you were generating the plus charge from already something which is positive here, so making the things even more worse for this situation. So this is deactivating. Okay, so ortho para positions will be deactivating. However, if you go ahead and attach it on the meta, you will never get directly under the carbonyl group. Okay, and thus it will be a less destabilizing situation, and thus will cost less energy, and hence it would be more favorable as compared to the orthopara positions. So we learned that electron withdrawing groups, they are deactivators, and thus they will be directing the groups towards the meta position. And then electron donating groups like OH, NH2, CH3, they are the activators. We are talking for the electrophilic aromatic substitution. They will be activating the group, and thus they are orthopara directors. Okay, this is it for this video.